today's speaker, Jaehyeon Ryu from Department of Mathematics, Yuha Women's University. The title of his talk is really Spherical Maximal Functions and Two-Step Nilpotent Groups. Okay, with this, I would like to invite him to deliver his talk, and I also request all the participants to mute their microphones. Okay, over to you, Ryu.
Okay, can I start now?
Yes, you can start.
Yes.
Yeah.
Okay. Thank you for the kind introduction, and thank the organizers for inviting me to this seminar. I'm very happy with this opportunity to present my results here. Okay, let's get started. So I'd like to begin my presentation by introducing spherical maximal function briefly. I think that most of the audience here are familiar with this subject, but let me briefly introduce this concept. Okay, spherical maximal function is defined as the supremum over t, the positive t of this averaging operator. So the spherical maximal function denoted by m sub s is defined like this, and here the a sub st is the averaging operator over the sphere, the unit sphere. So, and here the sigma is the surface measure supported in the sphere. This is the definition of the spherical maximal function. This spherical maximal function has been studied by many authors, including Stein, Bourgain, or what kind of the Seeger Sok. As far as I know, the boundedness property, the LP boundedness property of this operator was initiated by Stein in this work. In this work, Stein proved that the spherical maximum function is bounded on this LP space if P is greater than this number, and if D is greater than or equal to 3. This was very interesting result. And later, Bourgain and Seeger Sok proved that Stein's result in not in this setting, but in this set, in the setting of D is equal to 2. In Stein's work, he didn't prove this boundedness result in this case. This case was regarded as the difficult case at the time, and indeed it was. Actually, Bourgain's proof is very different from the Stein's proof. Actually, he used some geometrical argument. I don't know about clearly, though. However, later, working out the Seeger Sok proposed another proof of this result, of the same result, using the local smoothing estimate. And later, another problem regarding the boundedness property of the spherical maximal function was studied by Sok and Ryu. They studied the LP-LQ boundedness property of local spherical maximal operator. I like to mention that if we consider global spherical maximal operator, not the local one, then the LP-LQ boundedness fails to hold when P is different from Q. So there is no meaning of studying boundedness property of a global spherical maximal operator when P is not equal to Q. And finally, or lastly, Duane Vega, Lacey, and Lee was also studied problem, slightly different problem about the boundedness property on a weighted LP spaces. So this is the brief introduction of the spherical maximum function. Okay, so now let me move on to next slide. In this slide, I like to introduce Heisenberg group, which is one of the main subjects of my talk here. Heisenberg group is the very well-known Ryu group, one of the very well-known Ryu groups. This is the set. This is defined as the set, this one, I mean the R to n times R, equipped with this multiplication law. Here, J is defined as this one. I mean this matrix can be shown to be a skew-symmetric matrix without any difficulty. So this is the skew-symmetric matrix. Skew-symmetry. Skew-symmetricity is important throughout on my talk. And here are several important remarks about the Heisenberg group. First, the Heisenberg group is a simply quantitative Ryu group. So it's the Ryu group, right? And secondly, this Heisenberg group satisfies this parabolic scaling structure. This means that if we define delta sub t like this, then we can show that this relation holds without difficulty. Yeah, this is actually the result of a calculation. And lastly, so you may notice that the Heisenberg group is written like this. I mean the R to n times R. And here, R to n, R to n is called the horizontal part of the Heisenberg group. And the second part, and the R, the real number, is called the vertical part of the Heisenberg group. So to visualize the Heisenberg group, it can be understood as this diagram. Oh, yeah. So, okay, let me draw some very simple diagram. And here, this one, I mean the horizontal plane, this horizontal plane can be understood as the R to n. And here, this one, this axis, can be understood as R. So in this sense, R to n is the natural choice of the Heisenberg. So natural choice for the horizontal plane. So this is why R to n is called the horizontal plane and R is called the vertical part. Okay, so we now move on to the next slide. So in this slide, I like to introduce a Nevo-Thangavelu maximum function. The Nevo-Thangavelu maximum function is an analog of the spherical maximum function. So this is the analog of the spherical maximum function in Euclidean space. In Euclidean space. So what is the Nevo-Thangavelu maximum function? This is the maximal. This is defined as the maximum over t, positive t, of this operator. Here, mu stands for the surface measure supported in the sphere, but here is the important thing comes. The sphere should lie on the horizontal plane. So sphere looks like this. So sphere is like this. So this is the horizontal plane, and the sphere lies on the horizontal plane. This is the main difference between the ordinary spherical maximum function and the Nevo-Thangavelu maximum function. Okay. So after defining this, we can discuss some boundedness property of the Nevo-Thangavelu maximum function. Here is the explicit representation formula of the Nevo-Thangavelu maximum function. Indeed, using the multiplication law I introduced before, we can write the MF, I mean the Nevo-Thangavelu maximum function, like this, I mean explicitly. As far as I know, the boundedness property of the Nevo-Thangavelu maximum function was first studied by Nevo and Thangavelu in 1997. Here, the authors proved some results about pointwise algorithm theorems for radial averages. Okay, since Nevo and Thangavelu introduced this operator and proved some boundedness property, this problem has been studied extensively by many authors. So here is the list of the related results. First, Nevo and Thangavelu proved that the Nevo-Thangavelu maximum function is bounded on LP space if P is greater than this number, when n is equal to or greater than 2. You may notice that they couldn't cover this case. Yes. Actually, I will tell you that this case is the most important, most difficult case. As far as I know, there has been no result on this case. I mean, regarding the boundedness property of the Nevo-Thangavelu maximum function. Later, Müller and Seeger and Nevo and Thangavelu in the same year, in the same year, they proved that Nevo-Thangavelu maximum function can be extended to a bounded operator on LP space for P greater than this one. So basically, what they did was to extend or improve this result. You may easily notice that this result is smaller. I mean this one is more restrictive than this one. So this one is wider than this one, and they also proved that this range is optimal. So the boundedness range of P is optimal. So they essentially proved the boundedness property of the Nevo-Thangavelu maximum function for P in an optimal range. However, they couldn't cover the case when n is equal to 1. Okay, later, Russe and Seeger and Shrivastava studied another problem, like LP-LQ boundedness of a local maximum operator. This is very similar to the aforementioned result, the result I mentioned before for the Spherical maximum function. So they actually studied the local maximum operator is bounded from LP to LQ space for certain pairs of P and Q. And then Bertrand, Guo, Hickman, Seeger in 2022, they studied the LP boundedness property on Heisenberg radial functions in the setting that n is equal to 1. This is slightly different from the LP boundedness property of the Nevo-Thangavelu maximum function. Actually, they restricted the class of functions to radial functions. So considering only the Heisenberg radial functions.
So what is the range of P in this case for radial function for this case n is equal to 1?
So they proved that M is bounded if P is greater than 2. I'm sorry. P is less than 2. I'm sorry. Let me see.
P greater than 2.
P greater than 2, right. Yeah, right.
So, and it is optimal or not? Or
this is optimal. This is optimal.
Result. And for for in general functions, they have not proved anything. Or is there any result?
No, we don't know. We don't know
We
yet.
don't know till now. Oh, this is nice.
Yeah.
Okay.
Yeah. We don't know in general case.
Okay. Thank you.
And then Li and Li proved that considered the boundedness property on Heisenberg radial functions in the setting of the LP-LQ boundedness of the Nevo-Thangavelu maximal function. So they actually obtained LP-LQ boundedness result for the Heisenberg radial functions when n is equal to 1. And finally, lastly, Sherry, Hickman, Wright, and Kim and O consider the boundedness of the Lacunari maximal function defined like this. Okay, so here is the history of the Nevo-Thangavelu maximal functions. Now, I'd like to move on to the next slide, which is about the two-stem nilpotent group. Okay, so I'd like to so the topic of my talk was about the two-stem nilpotent group, but I haven't introduced what it is. So in this slide, I would like to introduce the two-stem nilpotent group. The definition of the two-stem nilpotent group might look slightly complicated or technical, but it's simple. So okay, let me start. So G denotes a regroup. Then G is called a two-stem nilpotent if there is the power of normal subgroup of length 2 or length 3 such that G1 and G2 these commutator relations. Okay, and there is a well-known result about the two-stem nilpotent group. Every simply connected finite-dimensional two-stem nilpotent group admits a step 2 stratification. What it is? What is it? It means that its Lie algebra G is splitted as the direct sum of two vector spaces, such that each vector spaces, I mean V1 and V2, satisfy these commutator relations. The regroup satisfying this property is called Carnot group of step 2. So throughout my talk, I will focus on boundedness property in this setting, I mean the Carnot group of step 2. So so far, I have introduced the Carnot group of step 2. However, from this definition, I mean, I don't know. You may still have a very little sense of what it looks like. However, using Baker-Campbell-Hausdorff formula, we can have the very clear and explicit representation of this two-stem nilpotent group. Actually, using Baker-Campbell-Hausdorff formula, we can identify this Carnot group of step 2 with this set. So, okay, so this can be identified, this set, but equipped with this multiplication law. So you can think of this Carnot group of step 2, whose definition looks slightly abstract, but you can think of this Carnot group step 2 as this set with this operation law. So this is very explicit. However, the multiplication law is slightly general, slightly different from the operation in the Heisenberg group. I mean, the multiplication law looks similar to the one appearing in the Heisenberg group, but the operation is more general. Here, the point is the J. The J means the pairs of the skew-symmetric matrices, where each skew-symmetric matrices doesn't need to be invariable. I mean, they can be singular, so that J1 can be like this. You know, J1 can be okay. For simplicity, let me assume that D is equal to 2. Then J1 can be D1 2 M is equal to 1, then the J1 should be the 3 by 3 matrices. So they does not need to be invariable, which means that J can be like this: 0 0 0 0 minus 1 1, like this. They should be symmetric, but they don't need to be invariable. So this is the main difference from the Heisenberg group and the two-stem dependent groups. So in the Heisenberg group, the skew matching matrix should be invariable, but this is not the case if we consider the general two-stem dependent group. Okay, we move on to the next slide. So we can naturally define the Nevo-Thangavelu maximal function on general two-stem dependent groups by using this multiplication law. So the definition, the explicit definition given like this. So here, M, we continue to have the same notation as we had in the Heisenberg group setting, like M. So M denotes the Nevo-Thangavelu maximal function on general two-stem dependent group. Here, MF is defined like this. Yes, this is the averaging operator over the sphere, but lying on a horizontal plane. This is important point. However, the boundedness property of the Nevo-Thangavelu maximal function in the general two-stem dependent group has not been studied much. I mean, so the boundedness of the maximal function has been investigated deeply in the Heisenberg group setting, but the boundedness property in the general setting has not been studied much. So this was the one motivation of the main result of my talk. There are two remarks I'd like to give. The first thing is that Miller and Seoul studied a similar problem. They actually studied the boundedness problem in the setting of the Métivier groups. The Métivier group is the class of Lie groups, including the Heisenberg group, but yet narrower than general two-stem dependent groups. So Métivier groups is the subclass of the general two-stem dependent groups. So they actually considered the boundedness problem in a general setting, but not too general. So they didn't consider the setting of the general two-stem dependent groups. However, recently, in last year, Ryu and Yan considered this problem in general two-stem dependent groups. I mean, where the skew matching matrix allowed to be degenerate. So in this setting, they prove this result. M is bounded for P is greater than this number. However, they obtained partial result. The reason is that they only consider this case when M is equal to 1 and D is greater than equal to 4. And I like to remark that even though they did very good results, they did very good work in their results. But I like to remark that this range is not optimal. And in this slide, I'd like to present one of the main results. I worked on this problem with Andreas, and I was able to prove the boundedness property of the Nevo-Thangavelu maximal function in the setting in the general two-stem dependent groups for every M and D greater than or equal to 3. So we extend the range of D and M. And furthermore, we are also able to obtain an optimal range of P for the Nevo-Thangavelu maximal function is bounded on LP space. So the statement is given like this.
Can you go
here
back
are
to the last result? Let us see.
this one.
Okay, so they are taking this d greater than equal to 4, but in your case, you are taking for n m is equal to 1. But in your case, you are taking any m, right?
Yeah, I can take any m.
Okay, and what about this d by d minus 1? Is this endpoint? It is not bounded, or you do not know it.
Yeah, it's not bound. No, it's not bounded when p is equal to d
So
over d
by
minus 1.
Okay, thanks.
So yeah, in this sense, this range is optimal.
Okay.
So yeah, thank you for making a good point. Actually, yes, this was the first remark. If t is less than this number, yeah, then you can find some suitable example showing that the MF is not the Nevo-Thangavelu maximal function is not bounded on LP space. Another small remark is that the same assertion, I mean the same statement, continues to hold even if we choose another hypersurface other than the sphere. However, the surface should satisfy certain geometric conditions. The second main result is about endpoint estimate for local maximal operator. Yeah, I just before mentioned that the Nevo-Thangavelu maximal function is not bounded on LP when P is equal to this endpoint. I mean, P is equal to D over D minus 1. Then the strong LP boundedness does not hold. However, if we look for an restricted weak type estimate for a local maximal operator, then the result becomes different. We can prove that the local maximal operator is bounded from this one to this one. I mean, actually we prove on restricted weak type estimate for local maximum operator at this at the endpoint. I mean, the important thing is that so even though it's written that it's written like this result holds for all p greater or equal to this one, but the important thing is that it holds when p is equal to d over d minus 1. So this is the second result. And I'd like to make another one remark, one additional remark regarding this one. Recently, restricted weak type estimate, the same restricted weak type estimate for the global maximum operator. Actually, in our result, we only consider the local maximum operator, but we in the paper we proposed a conjecture that the endpoint estimate, I mean the local restricted weak type estimate, should hold for the global maximum operator. And recently, John and Kim proved they submitted their paper to archive about the proof of the restricted weak type estimate for the global maximum operator. And okay, we now move on to the next slide. Here is the second main result.
One thing, for d is equal to 2, you don't have anything, right? Or
yes, right. Yeah, yeah. This is the most important, most difficult case. You made a very good point, but unfortunately, sadly, no, we don't know yet.
Okay.
Okay. Yeah, thank you. Yeah, thank you for comments. And the third result is about the almost ever convergence. Yeah. An important application of the boundedness property of the spherical maximum function was that we can prove on almost every convergence result using the boundedness property of the spherical maximum function. So we did the same thing in this setting. So we proved that when p is greater than this one, then the averaging operator goes to fx almost everywhere as t goes to 0. To prove this almost every convergence, proving this result was not sufficient. Actually, we proved this estimate. I mean, in the vector space dispersions. I'd rather not explain these estimates in the details and let me go to the next slide. Okay. So from now on, I'd like to introduce the.
Sorry, can you go back to the previous page? Okay, so what is this thing? Theorem, second theorem.
Basically, this one?
Yeah. So what is this expression? I don't know. Something. Yeah.
So this is about the LP estimate of this maximal operator. However, the maximal operator looks different from the Nevo-Thangavelu maximal function. This is a variant of the LP bound is LP estimate for the Nevo-Thangavelu maximal function. This looks a little technical, but we have to go ahead.
So you really, for almost everywhere convergence, you have to show this theorem, or you need this theorem, or what?
We need this theorem.
Okay. And for the maximum, actually from the maximal, the boundedness of maximal function, you will not get this result.
Yeah. This I don't think that this is sufficient to prove this one.
Probably at the end, you should you may explain this thing a little bit. Why this is not really giving you this almost everywhere convergence. Maybe at the end. Okay.
I'm sorry.
So why this previous theorem is not sufficient to prove this thing? Almost everywhere convergence.
The important thing is that we don't know.
Okay.
We don't know that we don't know whether this one is continuous in T by merely using this one. I'm sorry. So the important thing in the proof of this is to show that this is continuous function in T. So this was the one important step in proving this one, this kind of result. However, we had the difficulty proving this one by merely using this LP bound result. For that, we had to modify the LP estimate for the Nevo-Thangavelu maximal function a little, so it looks like this.
Okay.
Just one more question in this regard. So on the Heisenberg group, proving the maximal function boundedness is enough to give the pointwise convergence, right?
I'm sorry. I don't know clearly. Yeah. I don't know. I'm not familiar with this stuff. But you're right. Yeah. Perhaps you're right. Yeah.
Okay, please go ahead.
So does it answer your question, or?
No, my question is even on the Heisenberg group, just not on a general group, on a Heisenberg group, proving the boundedness, is it enough to conclude the pointwise convergence, or there also you need a stronger result like this on the base of space?
I'm sorry, I don't know.
Yeah. No problem. Please go ahead. Go ahead.
Okay, thank you. Yeah. I'm sorry. Okay, so from now on, I'd like to introduce the proof briefly. So basically, here I'd like to present outline of the proof. So the first step is the reduction. Okay, so we recalled M is given like this, where mu is the directed surface measure supported in the sphere lying on the Heisenberg group. So the first reduction is the typical one. I mean, the standard reduction. I mean, there is the sphere in the horizontal plane. Yes. Yeah, it looks a little bit weird. Okay. So sphere, and what you want to do is to decompose the sphere into finite pieces, right? So that we can only consider each patch of the sphere. This is a standard reduction, usually considered in the setting of the Euclidean space, but we can do the same thing in the case of the general two-stem dependent groups. And furthermore, this is another standard reduction. In the Euclidean space, we used to rotate this patch so that it position like that. I mean, the position it's located like this. I mean, the let me say this one is the XD axis. So this axis stands for the RM, and this one stands for the X prime, and X prime means the point in RD minus 1, and let me say this one is XD. And so that we can rotate this patch so that the XD axis, oh, I'm sorry. Okay, let me say this one. Okay, you can rotate this one to locate in this position. So that the XD axis intersects with the patch transversely, right? We can do the same thing. We can do the same thing in the case of the setting of the general two-stem dependent groups. So what it did was to decompose the sphere into finite pieces and rotated each patches to locate it so that the XD axis intersects transversely, right? So this can be summarized, right? And this can be summarized like this. I mean, the sphere measure mu can be made. We can reduce that. We can reduce the situation to the situation where the surface measure mu is given by this formula. And here, the surface is the graph. Is the graph of the function, this function. And G here satisfies this relation. This relation actually means that the x1 axis, transfers this patch. This can be proven by using the rotation and the shear transformation. Yeah, we have to consider shear transformation because we consider this problem in the setting of the general two-stem dependent groups. Okay, we now do another reduction. This is the one here reduction we made in our work. The conclusion is that the skew symmetric matrices can be assumed to be linearly independent. Yeah. This means that this one, I mean the linear combination of the skew symmetric matrices never vanishes or non-zero zeta. So this means that the linear combination of the Ji satisfies this boundedness relation. This one, it's not difficult to explain how we deduce this result. However, let me skip this part because it's a little bit technical. However, this can be done by using the singular variable decomposition of these matrices where the Ji is written like that, written like this. Okay, let me skip this part. And the second, okay, here is the second step. In this step, I like to do some dyadic frequency decompositions of the measure. To begin, I like to write the measure like this. So you can easily notice that this one is equal to the Dirac delta, x1 minus g1 x prime x upper bar over line x over line x. So by using the Fourier transform, we can express this distribution like that. This is the starting point of our analysis. And here, at this point, I'd like to decompose this integral diadonically. The first step is to decompose the corner with respect to the size of sigma tau. So you can easily notice that this square sum, the square root of this square sum is equal to the size of the sigma tau. So this is basically the same as the Ricciardo-Perry decomposition. And now I like to decompose it further, and by introducing this additional cutoff function. So this cutoff function, the reason why we introduce this cutoff function comes from the fact that the sphere is lying on the horizontal plane. So basically, by decomposing this decomposition, by making this decomposition, we cannot analyze. We cannot analyze. Okay, merely by making this decomposition, we cannot analyze exactly. I mean, clearly the structure of this corner. To analyze this corner more sophisticatedly, we have to introduce this additional cutoff function. So this is the decomposition of the corner, and UKL is defined like that, so that we can write U as this sum. So this is the decomposition process, and then this decomposition allows us to obtain some estimates for each individual pieces. So we now reduce the problem to the situation where we can only estimate each individual pieces, like this one. So we need to obtain some good LP estimate for this one, then the problem will be solved. So this is the very basic strategy. However, however, there is some difficulty. There is some difficulty if we approach to estimate this maximum operator directly. So what does it mean? I mean, we would like to transition the problem. So we would like to change the problem. So what we want to do in this slide is a transition from the global to local. So we would like to transition the global maximal operator to local one. So here the local means that the local maximal over T. So how we can do this? So to do this reduction, we note this one. So let us observe that MKLF is the supremum over all T. However, it can be said like this. It can be said as a sort of dyadic decomposition in T. However, yeah, even though it's slightly different. And we can remove this supremum by changing it, by replacing it with the L2 norm over N. This is one typical embedding property. And we also want to erase this supremum either. So how can we erase this supremum? This can be done by using this sober embedding. So using this sober embedding, we can change our problem to obtaining a kind of local smoothing estimate. So this is the result. This is the basic idea. Even if we obtain this estimate with bound B, with the good bound, bound B, then we are done. So this is a very basic, very brief explanation of the proof of this step. However, I'd like to remark that if we take the derivative to this directed measure, then it is invertible. It is inevitable for us to get this loss of this vector. Yeah, this can be regarded as a loss. This is inevitable if we decided to take the derivative in t here. However, it turns out that it's acceptable. Yeah, we are okay. Yeah, we are okay with having this loss. So we can, this one does not matter. This is the point. So doing so, we can erase the supremum over t over this one and this one. So this is the basic idea. And the basic strategy in obtaining these estimates to use the real interpolation between P1 and P2. For P1, P is equal to 2, equal to 1, a key ingredient of the proof is to use the cardinal geometric composition adapted to Cardano-Theodori balls in two-stem nilpotent groups. This balls is basically the natural ball. This is the natural ball in the setting of the two-stem nilpotent groups. And to obtain these estimates when P is equal to 2, we exploit almost orthogonality among these summands. I mean, among these summands over n. So over n. So to make this argument work, we need to establish. We need to first. We need to exploit almost orthogonality among the summands, and in addition to this, we also have to obtain a local L2 estimate for each individual piece. So the problem is now reduced to showing this local estimate for each individual pieces. So this can be regarded as a kind of the local smoothing estimate because the t, there is no supremum in t, but the integral over t. So this is the main estimate for our result. This is the main ingredient. And I like to make one remark. Once we prove this estimate, then the following using the Brueging's interpolation trick, Brueging's interpolation trick, and so on, we can prove the endpoint restrictive weak type estimate at the endpoint for a local maximal operator. Okay, we now move on to the next slide. And this is the final step. So basically, the proof of proposition relies on a real interpolation. I mean, the Martian-Case interpolation between two cases, P is equal to 1 and P is equal to 2. The case where P is equal to 1 is easy to deal with. Actually, the corresponding estimate, we can easily obtain this estimate using interpolation by parts many times. So interpolation by parts can do, is enough for us to obtain desired estimate. However, when we consider the case P is equal to 2, then the problem becomes difficult. To treat this case, we need to make additional reductions by using shear transformation and differential shear. This argument is now well known and standard. And actually, this estimate, I mean, the using shear transformation and Planck's theorem, was already considered in the work by Mueller and Seeger. However, the real problem lies in a different place. Okay, as a result of using the shear transformation and Planck's theorem, you can reduce the problem to showing this one. This is the L2 estimate for this operator, which looks slightly different from the original average operator, though. But it comes from the original average operator. I mean, it comes from the F star mu k L t. It comes from the L2 estimate of this one. So the goal is to obtain this L2 estimate for this TKL zeta F. Okay, how could we obtain this estimate? Our strategy for proving this estimate can be divided into two steps. One for small l and the other for large L. The second case is much more involved. I mean, when L is small, then we can relatively then we can obtain the desired estimate relatively easier. I mean, the estimate follows from the standard t-test argument. So in this case, the phase function is non-degenerate, which means that the mixed Hessian of the phase satisfies this condition. So we can use the generalized function theorem or Helamander's L2 theorem to obtain this result. And this result is exactly the same as this one, because when L is not large, then this one can be regarded as the constant. So this one is obtaining this one is enough, but this one actually gives the desired bound. So now we consider the large L. This is the hard case. If we consider this one, then the problem becomes more difficult to address. The main reason is that if we look for this case, then the phase function exhibits almost degenerate behavior. I mean, the phase function does not satisfy this good condition anymore. I mean, what does it mean? It means that some entries of the mixed Hessian can be very small. Yeah, can become smaller and smaller as L increases. I mean, I can't remember the exact factor, but the sum of the entry looks like 2 to the minus L or something. So if L is very large, then this entry can get very small. So what does it mean? It means that the lower bound of the determinant of the mixed Hessian can be very small. Like we obtain like this one something. I'm sorry. So let me say ML. No, it's not M. So like I don't know. So 2 to the minus low L with some low. So this is the problem. So we had to devise some method to address these phenomenon. So to analyze this phenomenon, we had to make a final decomposition in X and Y spaces. So we decompose the function into more elementary building blocks, and then we use the almost orthogonality argument. Basically, we use the Kotrach-Stein lemma. But the point is to decompose the X and Y spaces so that it is an appropriate choice of analyzing the structure of this operator well. So this is the main step of the proof. And so I have 4 minutes left, right? I originally was supposed to end my talk here, but basically when I prepared my talk, I was afraid if I have too much time left at this point. So I prepared 2 or 3 slides, but I realized that I have not much time left. So let me skip this part. So basically, this one is about my ongoing project. But let me skip this part and let me finish my talk here. Thank you. Thank you so much.
That's right. Thank you, Ryu, for a nice talk. Are there some questions from audience? So,
okay, so I have one question.
yeah.
Can you go back to that proposition? I think step 3 of your proof. The local smoothing estimate.
Yeah.
Yeah, because yeah. So is this estimate sharp?
No, I don't think it's sharp.
Okay. And
but,
for D, yeah, okay.
Yeah, I just wanted to mention that an interesting point is that it is sufficient. This assertion is sufficient to give the desired boundedness property of the Nevo-Thangavelu maximum function, even though it is not sharp.
Yeah, okay. And if one can improve this bound with respect to L, because it is D minus 2, so that's why you cannot get bound for dimension 2, right? Because it vanishes. So if one can improve this estimate to the power L D minus 2 by P prime plus some positive number, then maybe one can get the boundedness in dimension 2.
Perhaps not. Perhaps no. I think that when d is equal to 2, then we cannot. So okay, the thing is that the bounds, this vector. Okay, how can I say? Okay, so the thing is that when d is equal to 2, then the maximal the estimate for each individual pieces, I mean for the maximal operator, the L2 estimates should have the bound a bound as a constant. So this is what I know. So since the bound is given as the constant, we cannot sum these L2 estimates for K and L. So the estimate, I mean using the triangle inequality. So yeah, when we approach to sum this one over K and L using triangle inequality, then the MF should be very large. So this is the problem when in the case of D is equal to 2.
Yeah.
But I don't know. Yeah, I don't know. We can obtain a better estimate in 2-dimensional case, and this improvement should yield some good positive results in this case. I don't know. I'm sorry.
Okay, thank you.
Okay, so are there any other questions? Okay, if there are no more questions, let us unmute and thank the speaker for a nice talk. Okay.
Thank you. Thank you so much.
I am ending this session now.
Thank you, Jaehyeon, for this nice talk.
Thank you.